Hi everyone, welcome back to Z Physics. Today we are going to be looking at the basic features of waves. Okay, well, let's get started. The first thing that we need to do is to imagine that we have a wave, and for instance, this could be something really simple like a string that we fix on one end and then move the other end up and down to produce a wave of certain shape. The first quantity that we're going to define is the displacement. Now, the displacement of a point of a wave is its distance to the equilibrium position. For instance, if I was to pick, let's say, this point of the wave, the distance from the line of equilibrium will be this much. However, if I was to pick a different point, let's say this one over here, it will have a different displacement, i.e. it will have a different distance to the line of equilibrium. Notice that there is a maximum value of this displacement, which I'm going to draw right now, and this is known as the amplitude of the wave, which is the maximum displacement from the equilibrium position. In this case, this is represented by this line, and this is the amplitude of the wave. Notice that the amplitude can be both positive in this region, but it can also be negative in this region over here. Let's have a look at what the wavelength is next. First of all, the wavelength is the distance traveled by the wave during one time period. We can formally define this as the distance between two consecutive points on a wave with the same phase. Now, what does that mean? For instance, let's take this point over here at the beginning of the wave. The next point with the same phase will be the point at which the wave starts to repeat itself. For instance, that's not going to be here because at this point the wave is going down into the negative displacement region. However, as soon as we reach here, the wave is about to start to repeat the pattern. So for this wave, the wavelength will be lambda, and it will be this distance over here in green. Normally the wavelength is given the Greek letter lambda. Up next, let's define the time period, which is normally given the symbol t, and the time period is defined as the time to complete one full oscillation of the wave. Next, we'll be looking at the frequency f. This is defined as the number of complete oscillations per second. We can find the frequency as 1 over the time period. It also follows that the time period is 1 over the frequency. Now, how does this equation work? For instance, imagine that our time period was half a second, so that would mean that one full wave cycle would take half a second to complete. In this case, the frequency will be 1 over 0.5, which will be 2 hertz. The unit of the frequency is the hertz. Additionally, the base unit of that, because frequency is 1 over the time period and the time period is measured in seconds, 1 hertz is actually equal to 1 over seconds, or additionally we can write this as s to the power of -1. And finally, we're going to define the speed of the wave, which is normally given the symbol v, as the distance traveled by the wave per unit time. Okay, folks, so those were the basic features of waves that we're going to be using in wave motion. If there are any questions, feel free to drop a comment. Thank you very much for watching, and I hope this was useful.